Hello everyone. My name is Leo Martinez, and I'm a postdoc student of Miriam Lemelins in Sherbrooke, Canada. First of all, I want to thank you all for this amazing amazing conference that we do on this date, because it's enabling us to share our work, and that's really nice, I think. So. I want also thanks my co-author, because they did part of the job, so most of the job actually. So I'm happy with that. And yeah. So during this presentation, originally I prepared a 15-minute presentation but since Stuart kindly asked me if I wanted a 13 minute slot, I added a small condensed resume of my PhD. If you guys are interested, it will be after that. For the first part, I will present the MorphoPy the workflow that we did, which is kind of similar of what you other guys do, especially you, Dylan. You'll see. Originally, this study take its roots into the lunar vertex landing sites analysis, which is, I'm sure you know, in the Rhino Gamma lunar swirl. Lunar swirls are probably one of the most enigmatic geological morphological features that we can spot on the moon. Even today, their origin are highly debated, and there is a lot of theories. It's not completely we don't completely understand how it forms and that, but I will not discuss much about that in this presentation. I will let Ilem do it in this presentation this afternoon. But anyway, in the origin of this project was the need to quantify crater morphometry in the Rayner Gamma area. Of course, in literature, there's a lot of crater morphometric studies, as you guys know. We cite a lot before, but we wanted to make something which was kind of a reference using the best studies in literature. So we wanted to establish a standard morphometric analysis, and we built a tool for that to quantify the morphometric parameter of crater on the moon, but also on other planetary surfaces. We wanted our tool to be easy to use, you just provide a DTM and a crater database, which can be made manually or automatically, and which you just pick and play and you see the results. So for the method, as Dylan presented, we did kind of the same approach. We created one profile file, one topographic profile each 10 degrees in the crater using the digital elevation model. And then we looked for the highest elevation points on the profile to draw the crater crest like this. But that's not it. With these 35 profiles, we were able to calculate a few morphometric parameters, such as the mean crater diameters, the crater depth, the depth to diameter ratio, all the associated measurement uncertainties, the circularity and eccentricity of craters, the wall slope, and we introduced a new freshness / degradation index for our craters. So for the diameter, it's kind of basics. We just took the maximum, the highest point of we calculate the distance between the highest points of one profile and the highest point of the adjacent profile. And this gives us 28 distances, since we have 36 profiles, and we just basically did the mean of these 18 these 18 profiles to have the diameter of the corresponding craters. And we used the Rachel Over paper to calculate the uncertainty corresponding to this quarter, this dimension vision. Also for the depth, same things. We took the mean of all the difference between the highest point of the profile and the lowest point of the profile, and it gives us the depth of the corresponding craters. We use also the Hoover and all the Hoover and all 2024 formula to calculate the uncertainty of the depths, and of course with this with the two depth and diameter we calculated the D2D ratio and also the corresponding uncertainty between the D2D ratio. We also calculated, we used the Julie Stopper 2017 method to calculate the wall slope of the craters. So basically, we took a range between 20 and 80% of the profile to be sure to be in the wall of the crater profile. And with this simple formula, we calculate all the pixel to pixel slopes in the rim of the crater, and we did the mean of this of all those small slopes, pixel to pixel slopes, to have the slope of the profile, and then we use the median of all the slopes, the rim slopes, to calculate the slopes of the rim, the average wall slopes of the corresponding craters. It also comes with an uncertainties formula, but I will not detail it here because it's a bit it will be hard otherwise. And in the end, the freshness, we started from the Basilski 1976 papers / abstracts, which defined 5 morphological craters class. And I will detail here. It just basically classes craters with degradation rates. The A class encompass craters with clearly defined rim and very steep slopes. The AB, the rim is slightly flattened, but still the slopes are important. For the B, the rim are clearly smoothed, and the steeps start to be moderately the slopes start to be moderate. PC category, the steep slopes are very poor, and the rim is barely visible. And for the C category, there's no rim anymore and almost no slopes. This is how Basilski classified the freshness index. But basically, I've said you all of the detail just to show you that we can see 2 parameters that can be influenced by the freshness of the freshness states of the craters. Is the wall slope and the rim height. And so, but the problem with this for us with this freshness index is that it's there is only 5 classes, but how about something between A and AB, or A, B, and C, B, C, and C? It's not really easy to use, so we wanted to build a continuous freshness degradation scale. So in order to do that, we just basically built this formula. We just counted the number of profile rim we see, higher than 0. And we also computed the wall slope, the normalized wall slope in this equation, in order to have a score between 0 and 1. And I did this small animation to show that with this score we are able to quantify between 0 and 1 the percentage of degradation of craters. I did small plots to show you the results of this freshness scale. We can see on the left the C Basilevsky category. We can see it's a very the slopes are the wall slopes are very poor. The crater depth is very, very slow, even if the diameter is around like 100 meters. So it seems to work because the freshness we have is 0.14. So sounds like relevant with what we see. And on the right, you can see a very fresh crater. We see like rocky ejectas around, so it's like, yeah, and the slope are very steep. So we are like this sounds like to work basically. In order to like validate the process, we applied the whole thing to the Rhino Gamma area. So the detection, the crater detection database was made by one of our collaborators, Valentin Dickel. It detects more around like maybe more than 65,000 craters in the Rhino Gamma region. In 2 to 5 meter DTM, we took a threshold of 20 pixels, as Stuart explained, in order to be sure that our detections, that our measurements are like accurate. And so that's why Morphopile estimate the morphometric parameter of only like 22,000 craters on the area. So here we developed a robust crater morphometry workflow that can be used wherever you want on the moon, but not also. It takes only a crater database that you can like generate it manually or with a tool. And it takes also a digital terrain model, yes, and it enables to calculate all the parameters I told you. Okay. But still, there is, and you will probably highlight that, some limitation to this work because we need like to have like accurate DTM to do the job. But now, like you know that nowadays there is more and more pipeline to generate DTM from a pair of stereo images from NAC for the moon, but not also. So maybe that in few months, years, I don't know, it will not be a limitation anymore. And also future development that what we want to do is to apply this workflow to the moon south polar region, especially yeah, on area where there is DTM, of course. We want also integrate a few morphometric we will also integrate probably IA-driven crater detection and characterization algorithm inside the Morphopile tool in order to like make the detection analysis by itself. You just have to provide the DTM and it will like do the job. This led to a manuscript which is currently under revision, and the workflow will be released after the revision process, probably around September. So yeah, that's it for the Morphopile part. And so since I think I have like a few minutes left, I will like try to summarize my PhD in let's say 10 slides. Let's go. So for my PhD, we changed the planetary surface body. We will go to Mars, and I interested myself about like, is it possible to automatically make datation of the surface of Mars using like crater detection algorithm and stuff? That was the interest. So as you all know, craters are very like present in the solar system. There's a lot, and we can use them to make datation on planetary surfaces. You all know that, but the main problem with the crater datation, the crater counting based datation, is especially the crater counting step, because on this small example, we can try, if you want to count like crater bigger than, I don't know, let's say like 10 meters, it will be pretty not 10 meters, like 10,000 meters. It will be sorry, yeah, 10 kilometers. It will be easy. But if you want to count like craters more than like 1 kilometers or more than 100 meters, it will be much harder because there is like a lot more. So that's why we wanted to automatize the task. So for the crater detection, I will be very fast because I don't have much time. But we use an homemade faster air CNN model that we made on PyTorch. Using PyTorch, and we trained it on 100,000 images of CTX images of the surface of Mars. The training database was the Struct one, and so craters bigger than kilometers, and we archived with results. Very good results of accuracy. Here it's like a quick example. We published this work last year in a paper that you can have like just scanning the molecular code. For the crater characterization, the thing is that like only with detection the datation will not be precise because as you all know, when a big impact occurs, few like secondary craters are created by the first impacts. And so our aim was to classify the craters from like regular to secondary, but also on Mars we can have a lot of, but also on the Moon we have a lot of ghost craters, which we also want to remove for the datation process. So we needed like and we wanted also an automatic tool to classify craters by morphological features. So in order to do that, we trained a much more modern algorithm, the YOLO V11, only the classifier parts on the images of the CTX images of craters on Mars. And we archive also a good accuracy score, something which is close to what human can do. So, I mean, we can't expect to have better detection accuracy because you can't do better than what was in the training database. So we are really happy with this. You can also scan the QR code to access to the corresponding paper. Maybe it will not work because it was published like last week. So I don't know if the GUI was like working, but if you make a screenshot like next week, it will probably work. And with these two parts, like the detection and characterization, we're able to build an automatic datation pipeline. So basically, the user just provide a TIFF and a shapefile of the geometry you want to date. Can be whatever you want. And then our pipeline do the detection, the classification of the craters. It removes the secondary and the ghosts. Sorry, I missed a slide anyway. And it used the pipeline open crater tool pipeline made by the team of Freie University in Berlin to make the datation on the crater database. And it provides you a crater database of your region and the nature of the surface. Here it's a small application. We did that around the Zhurong landing site rover on Mars. So it detected a lot of craters. It took around 6 craters per second, which is nice. To do the job, and we wanted just to verify if it's work like for the datation, and so we compare ourselves. I let you judge. We compare ourselves with manual crater counting analysis made by Wu and collaborators in 2022. The waypoints, and we found ages that are like relevant with what Wu found. So we're kind of happy. It's a young region for Mars, like 3 billion years ago, and yeah, so just to conclude this part, during my PhD we developed a tool for make automatic crater dating surface, It can be used just to generate crater databases, but you can also make precise datation by removing all secondary and ghost craters. Our crater detection algorithm is reproducible, and you can like archive very good like detection results and classification results. So we are like very happy with that. And you can like theoretically apply it to other planetary surface. Just keep in mind that it has been trained on Mars. So on the moon, the result might be like a little less virulent, but still you can try to use it as a first tool. And of course, future work will be to extend the model to the moon and why not Mercury, incorporate it into the MorphoPy pipeline I presented you just before, and maybe incorporate more crater classes such as the presence of central peaks, flat floor craters, double ejecta layers, etc. And maybe, but honestly, I don't want to do that, but maybe it would be interesting to make a deep learning pipeline on few models to have an insight of like, are the models we used are good or not? And I think it's open the discussion of, in general, in planetary science, do we trust the model, the computer vision model, or do we in what way we trusted them or not? So I mean, it opened a discussion, and I'm open to discuss with you about that. Yes, that's it. Thank you all to listen this talk. You can scan the QR code to access to my personal webpage I did if you want more information about me or if you want to contact me. Thank you.
All right, looks like we have a question online to start us off.
Yeah.
Nice talk and congratulations for the work. I'm kind of interested in automatized precious estimation. Oh, this is just asking for your email.
Okay.
Never mind.
You can scan the QR code and my email is on my webpage, so you can. Otherwise, I put it on every slide here. So.
Great. Okay, Sierra, go ahead.
You mentioned like metrics that your database for Mars has. Like, what are some of those metrics and how do they compare to other data sets?
Oh, for the detection and classification, yeah. Sorry, I didn't have much time, so I didn't put slides about that. But of course, it's very important when we talk about like artificial intelligence based model. So we use the classical metrics that we found on literature. We didn't we didn't get fancy about inventing a new metrics. We wanted to be like the most simple and the most like relevant as possible. So we use the precision, the recall, the F1 score. We use, of course, for the classification, the accuracy, and we build like obviously the confusion matrix stuff to like see the intra-class error and more information. I can share you the preprint if you want to have the information. Yeah.
So how do you deal with different resolution DTMs? Like if we go to a NAC created DTM out of intuitive machines, even those vary based on the source imagery. You go to a different pipeline, the resolution of the DTM and construction of the DTM. So is that metadata passed on with the model, or how does it affect the
for the first part, I guess. So
yeah.
Actually we like kind of it's the user who provide the DTM, so like it's but we ask in the parameters of our algorithm to provide like the vertical uncertainty of the DTM. And it will, and so the pipeline will calculate the corresponding error using the vertical uncertainty of the DTM. So if the user provide like a DTM and he specify the vertical uncertainty corresponding to the DTM.
So if you were going to use it in the Reiner gamma area, I don't know if that was multiple DTMs.
Yeah.
You would process.
Yeah. It's one by one.
Divide up your work by.
Yeah, it was you. I mean, there is a 5 meter DTM of the world region.
Okay,
But there is also like a few 2 meters DTM in
yeah, so
the.
it'd be tempting to use those.
Yeah, we
Just in the back.
use like a 5 meter for 5 meter area and 2 meters for 2 meters area, and we in the end we merge the results in.
I just have a related comment to that. It sounded like you're using a fixed number of profiles for your measurements.
Yeah.
So
like, yeah.
one issue I ran into a few times is that using a fixed number of profiles, when you depending on the user, when you start getting to smaller craters, there's a risk of oversampling individual pixels. You might get duplicate hits on. And then at larger diameters, there's a lot of extra data there that aren't being picked up by the profile. So just a suggestion that we ended up doing is determining the number of profiles based on the size of the crater as a function of its circumference.
That's probably one of the perspectives that we need to work on, but still I say that we will not go to estimate the parameters of the craters for craters lower than 20 pixels in order to deal with that. But yeah, maybe that's like the solution we found like for the moment. But yes, probably we need to improve that. Thank you. Yeah.
I think there was a comment about automatically removing secondaries.
Yeah.
Can you elaborate on that? Sounds like a deep topic.
Yeah, it is. I mean, it took us time. Yeah, I was very fast. That was my PhD in 10 slides, so that was quick. So what was sorry, what you want me to comment on that part?
You just comment on.
Yeah, actually, as you guys always do since a long time ago, to make the difference between primary and secondary crater, you have a look at the context and you just check like if it's on a line or not. That wasn't what we made at the beginning. We just tried to actually I have a slide about that. We just for the data processing, we just I don't know if you want to see. Yeah, that's I hidden like slides. We just kept like first time we kept like an image of our crater, the training image around the crater with like a buffer in order to, and our guess was that if a crater was like kind of really alone in the middle of the scene, it will not be a secondary. And if there is much crater around, like on this image, probably like you can see.
You're not sharing anymore.
Oh, I'm sorry. Sorry.
Also, we're slightly running out of time.
Okay, so I need to be quick in my answer. So if the image is this, it's secondary. So it works like basically we can see in the confidence matrix this method works. We didn't have to check all the context to differentiate between secondary and primary crater. So I mean we were happy with that, and we didn't like add more like about that. Yeah. Sorry for my
Continue.
yeah to be
Yeah,
continued.
no problem. Thank you.
Sorry for time.
So one comment, you said that Thomas Heyer is from like Berlin or something. He's not, he's from Münster.
Oh, sorry.
Yeah.
I missed the German. Yeah, sorry. Thank you.
Right, well, let's thank our speaker one more time.